Okay, so I want to do a problem that I hope will sort of help you guys understand some of the principles we deal with in the homework problems a little better. So what I'm going to do is I'm going to do a problem. This is one I sort of had in my PowerPoint for Thursday and Friday, but maybe didn't get to with most classes. So we got two masses stacked up like this, M1 and M2. There is, let's see, there is no friction between M1 and the ground. So that means right down here, no friction. And there is static friction the coefficient is mu sub s between, well, I'll say between M1 and M2. So in here we've got some static friction, no friction here. So it's like these two blocks, maybe they're blocks made of wood. There's some friction there, and then like they're on ice, so very, very little friction, or we're going to pretend no friction. Okay, and there is a force pulling here. We're going to call that F. Okay, and we want to find maximum force F without M2 slipping. Okay, so to be clear, what we've got here, we've got these two blocks on top of each other, one on top of the other. There's friction between the two, no friction down here. We're basically grabbing the bottom one and yanking on it. So you can do this yourself by just taking two books and stacking them up on a table. You know, and I guess it helps if it's a really slick table, but even if there's some friction between the table and the bottom book, you'll still get the idea. That you're basically jerking on the bottom book, you're pulling on the bottom book, and how fast or how hard can you pull on the bottom book and still bring book 2 along for the ride, as opposed to just, you know, the bottom book slipping out and book 2 sitting there and then, you know, in midair and then going clunk. Okay, so what we want is for these to come along for the ride. We basically want no slip here. So if there's no slip, that means they're both going to be accelerating at the same rate. So we can say, I'm going to define the acceleration. Actually, I'm going to do that in a different color. Let's call it green. Acceleration, well, let's pick green, not call it green. I mean, this color is green. I'm not choosing to call it green. Okay, anyway, acceleration A goes that way for M1 and M2. So we're finding the case where, you know, where both books are accelerating at the same rate, sort of as fast as they can go, or as fast as they can be accelerated without, you know, this one slipping due to this force F. So, you know, there are two different ways to approach it. I'm going to sort of go through one way, and then I think probably I'll do a second video where I'll sort of explain an alternate way. So, what I'm going to do is first I'm going to draw just a separate M2 here. This I find is kind of helpful sometimes when you are, you know, you've got one of these multi-body systems that can be kind of confusing what forces are acting on what. So there's M2, and I'm going to draw the acceleration arrow in green. So it's accelerating that way. What are the forces acting on M2? Okay, so first of all, we have the force that we pretty much always have, which is gravity. Okay, so there's M2 times G. That's our weight. There's a normal force from block 1. So block 1 is underneath it. Block 1 is pushing up on it because these are in contact, right? So block 1 is pushing up on block 2. So I'm going to call that N12 for normal force between block 1 and block 2. Okay? And then there's a friction force. Now, here's the thing. Which direction, you know, because there's a normal force and we have a coefficient of friction, there must be a friction force. So here's the thing. Which way does the friction force go on block 2? Well, what we're doing, so let's come back and think about the problem. We're pulling on block 1 and we want block 2 to come along for the ride. Now block 2, Newton's first law says an object is not going to accelerate unless there's a force applied to it. So we want the block 2 to accelerate to the right. Well, it's going to have to have a force going to the right to make it do that, right? I mean, these are vertical, so they're not going to push it to the right. Something's got to push it to the right. Are there any other horizontal forces acting on this? No. So actually, that force going to the right that's pulling along has got to be the friction force. So there's our F sub F, which is the friction force between 1 and 2. And I guess I could write F sub F 1, 2, let me move that a little closer. So F sub F 1, 2 to signify that it's the friction between block 1 and block 2. There's no other friction in the problem because there's no friction here, but whatever. So there we go. Let's do an FBD for block 2. Okay, so first we're going to pick our coordinate axes. I'm going to do X, Y, the usual. I'll draw them over here again, why not? And then our FBD for block 2, which we're going to do here. There's our Y and there's our X. So block 2 here, this is pretty easy actually. So normal force between 1 and 2, M2 times G, and then we have the friction force between 1 and 2 pulling it along. Like I said, those are the only forces we got. Well, great. So let's say, let's come over here and do equations of motion. So sum of forces in the x direction is going to equal, well, let's just put them out there. So force of friction between 1 and 2, that's the only force we have in the x direction. So that's going to equal mass times its acceleration x. Well, it's accelerating in x, acceleration a, so we're just going to put ma in there. So, and I'm sorry, which mass is this we're talking about? We're talking about mass of block 2. So we're doing, these are equations of motion for block 2. So friction force between 1 and 2, mass of block 2 times block 2's acceleration. Easy enough. Okay, sum of forces in the y direction on block 2. So I'm going to write 2 here just so we remember we're dealing with block 2. Force in the y direction is, we've got the normal force going up, we've got minus m2g going down, and those are going to add up to, well, is block 2 accelerating vertically? No, it's sitting up here at the same level, it's not moving up or down, so 0. So now we can, let's see, let's move forward here. We can, from this equation, so we know that n12 minus m2 times g equals 0, so we can say that the normal force between block 1 and block 2 equals mass of block 2 times g. And many of the things you'll find here are really, if you stop and think about it for a minute, you'll realize they're almost kind of obvious. We're really using math to sort of discover obvious things. So for example, right here, the normal force between block 1 and block 2 is equal to really just the weight of block 2. That's what this is. So all that's saying is, well, block 2 has this weight, something's got to be holding it up, right? Or else it would be falling if not. And that's going to be the normal force. So that's just block 1 propping block 2 up, holding it up in the air. Okay, so easy enough. Now the friction force between 1 and 2, we can go back to our definition of friction. And what we're going to say actually, so the friction force technically for static friction is less than or equal to the coefficient of static friction times the normal force between 1 and 2. Well, now, and we know what the normal force between 1 and 2 is. Sorry, I just had a brain freeze there. And that's equal to m2 times g. But hold on, that's actually all times mu sub s. Let me write that in. Mu sub s, and then the normal force m2g. So I'm just taking this here and plugging it in for this n12. So that gives us our friction force. Now, with static friction, it can be less than or equal to. So mu s really gives like the maximum, mu s times normal force really gives the maximum amount of static friction you can have. I've explained this a little in class, but I just want to say it one more time. What friction tries to do, friction wants to stop any movement. Friction wants to keep these two things from slipping. When I say it wants to stop any movement, what it wants to stop is relative movement. So it wants to keep these two things from slipping. So when I say less than or equal to, that means, if it gives as much as it has to make these two not slip from each other. But what we said earlier was that we want the maximum force we can put on, the maximum force F we can apply to block 1 without M2 slipping. So when we do that, think about what happens when it slips. Then what happens when it slips is basically your friction is no longer enough to stop this thing slipping. So we're trying to find the maximum force, which means we're going to be counting on that friction to accelerate block 2 as much as possible. So we want the maximum friction out of block 2. So we can take this less than or equal to and really just make it an equal. So force of friction on between block 1 or on block 2, which we're calling F12, but we'll see in a minute that's basically the same, is going to be equal to mu s m2g. And then we can take this thing here, which we found. I'm going to take this here and plug it in for this up here. Okay, so what we get then is we get sum of forces in X, which is just the friction force. So we got mu s m2g equals m2a. Well, isn't that pretty? What can we do? We can cancel out the m2's for one thing, right? There's an m2 over there, boom, canceled. And what we get out of this then is acceleration. The maximum acceleration of block 2 is mu s times g. So already that's kind of an interesting result. It doesn't get us the answer, but it actually gets us very close, surprisingly. So let's see, what has it been, 12 minutes? So let's see, where can we go from there? Not quite to, yeah. So I'll tell you what, there are two different ways to go from here, and I am going to show you both of them, but in sort of different videos. I think I'm going to try for that. So anyway, 2 more videos to follow on this one, and I will be back in a minute. Pick one.